Hello guys, let's try and prove that pi by 4 is equals to this alternating series over here. So, I've given you guys a kind of hint, tan, which is tan. So, this series is related to tan x, but in fact it's related to arctan x, inverse tangent x, and the power series of it. And another way you can kind of guess why it's tangent inverse x is because you see pi by 4, and when you think of trigonometry you get tan pi by 4 is equals to 1. So somehow that matches, and let's move on and see the power series of tangent inverse x. So before we move on to the power series, you have to know that it involves a little bit of calculus and a big part of a binomial theorem. So here, tangent inverse x. This you can represent it as the integration of 1 by 1 plus x squared dx. Now you have this over here, and using the binomial theorem, you get that its expansion is 1 plus x squared plus x cubed and so on. So let me just show you how. So you can rewrite it as 1 minus x to the power minus 1. And here you can use the binomial theorem to expand this. So before that, the expansion of 1 plus x to the power n is 1 plus nx plus n minus 1 by 2 factorial x square plus n minus 1 n minus 2 3 factorial into x cube and so on. So instead of x you'll have negative x, and instead of n you'll have negative 1. So we'll have this, and the simplifying it you'll get this over here, and as you can see in the numerator you have 1 into 2, which is 2 factorial, 1 into 2 into 3, 3 factorial, and it goes on for all of the terms next. In fact, these two cancel in all the terms, so you'll get 1 plus x squared plus x cubed and so on. But one thing you have to remember is that the absolute value of x should be less than 1. Because let's say you have a number 2, and as you can see you'll have x squared, x cubed and so on. And if you get to a larger power like to the power of 5000, then you'll eventually reach to infinity. So simply, if modulus of x is greater than 1, it will diverge. But if I have less than 1, what happens is you'll get 0 point some number to the power of something, and eventually that number will be so high that that number will be approximately 0, and the next numbers after that will also be 0. Simply, if it is less than 1, it will converge. Here we have 1 by 1 plus x squared, but we need 1 by 1 minus x. So that's pretty easy, because here x just represents some number, any number of variable. So this x you can replace it with x squared, x cubed, 1 by x and so on. So you can read it as 1 by 1 minus and minus x squared dx, and simply over here instead of x replace it with minus x squared. So it will be like this, and this will be, after you simplify you'll get this, and now simply just integrate it. So it will be x minus x cubed by 3. So eventually you'll get this over here, which is very similar to what we had in the thumbnail. Instead of x we had 1. So you guys will know what to do. But there's one problem. This is an indefinite integral. That means after integrating all of these terms, you'll have a plus c at the end. But since this dot 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 represents the next term for this series, let's just write it over here. And we have this. And it's pretty easy to figure out the value of the constant. All you have to do is replace x with some number. So let's just try 0. Tangent inverse of 0 is 0. So this will be c plus 0 minus 0 cubed by 3 plus 0 to the power by 5. And all of the terms contain 0 in the numerator, so it will just be 0. That means you have c is equals to 0, and finally you get the power series of tangent inverse x, which is x minus x cubed by 3 plus x to the power 5 by 5 minus x to the power 7 by 7, and so on. Now, before we move on, we know for this, the absolute value of x must be less than 1. And this is for minus x square as well. So, instead of x, we'll have minus x square less than 1. So let's simplify this, because we have x to an odd power, but here we have minus x square. So let's just try to get it in terms of x only. So here minus is inside the modulus, you can just remove that. And here you can either use the modulus property right away, and this will be modulus of x whole square, but I'll just show you a quick proof. So x square is x into x less than 1, and this will be modulus of x into modulus of x less than 1. Yes, another modulus property, but this is easier. And this is square less than 1, and simply square root both sides. This that cancel, modulus of x less than 1. So what that means is, for this series as well, we need modulus of x is less than 1. But what we're trying to achieve is pi by 4, and that can only happen when x is equals to 1. So let me write it over here. If we plug in 1, what will happen is we'll get tangent inverse of 1, which is pi by 4, equals to 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 plus 1 by 9, and so on. And so here we have got our proof that pi by 4 is equal to this series over here. But in order to follow this rule over here, or this condition, what you'll have to use is limits. Yes, a bit of calculus again. So instead of x being 1, let's just make it slightly lesser than 1 such that it follows this condition. Let's say x approaches 1 minus, that means 0.999999 and so on. And since this is actually less than 1, it is true for this condition, and since it is very close to 1, we can in fact write it as tangent inverse of 1, which will still be pi by 4, and it will be 1 minus 1 by 3. Yes, 1 minus, but since 1 minus is so close to 1, we can write it as 1 by 5 minus 1 by 7 plus 1 by 9, and so on. And here, if you exactly put 1 over here, it will be an infinite term, infinite expansion, which is in fact allowed in mathematics without any condition. An example is the expansion of e, which is 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial, and so on. But here, for this series, we have a certain condition, we need to make it true, and hence we chose 1 minus, but in the end you'll get the same result, which is this, and there we go. This is our proof that pi by 4 is equals to this series over here. If you learned something new, please like and subscribe. Thank you.